guys, so this video is going to be about enzymes. So we talked a lot about what happens to the food that we eat in the last portion of our class. We know that the food that we eat is broken down into carbohydrates, lipids, and protein. This portion of the class is going to cover how that happens. So let's talk about a sugar called lactose. So first of all, what is lactose? Lactose is a sugar that's going to be found in dairy products. So for example, in milk. So you drink the milk, it's broken down into lactose. People, and not just lactose. So there are other things in milk. There are vitamins in milk, a little bit of protein, I believe. So there are other things in milk, but we're focused on the lactose. I just wanted to put that in case someone, is thinking that milk only becomes lactose. So what do people do who are lactose intolerant, or people whose bodies cannot handle the sugar in milk? So people who are lactose intolerant will lack an enzyme called lactase. And just a little vocabulary tip, sugars are going to end in OSE, while enzymes will end in ASE. But what is an enzyme? So an enzyme is a protein that is going to help two molecules react. Recall that the monomer of a protein is an amino acid. So enzymes are strings of amino acids, and remember that they're folded into special three-dimensional shapes because they're proteins. Without enzymes, the reactions in our cells would either never happen or they would happen too slowly to be useful to our bodies or to living things. So just a little bit of physical science, just a little refresher. So a chemical reaction, which enzymes help chemical reactions occur. A chemical reaction is the process of changing one set of chemicals into another set of chemicals. And this happens by rearranging the atoms in the reactants. So the starting materials will be the reactants, and the ending materials are the products. And this is the way that we write a reaction. So we write the reactions on the left side, and then we draw an arrow. That arrow says yields, and then we have our products on the right. What is going to happen in a reaction is that the bonds in the reactants are going to be broken and new bonds are going to be formed in the product. All right, so let's look at a graph, which is one way that we can show a reaction. So let's talk about first the parts of our graph. We have an x-axis, which is here, and we have a y-axis, which is here. I'm going to try to get a pen. Okay, so we have an x-axis, which is here. We have a y-axis, which is here. And on the x-axis, we are talking about time. So as time goes on, it's going to move this way. And on the y-axis, we are talking about the amount of energy. Okay, so let's just look at this first graph. So we have our reaction, and we start with the reactant. The reaction goes on, and we end with a product up here. So what happens is I see that the energy in my reactants, and here are the reactants, is lower than the energy in my products. Okay? The energy in my products is higher. That means that as this reaction happened, it took in energy. It's called an endothermic reaction. Now, let's look at my other graph. It's the same thing energy and time. So we have our reaction. We start with reactants, we end with products. And as time goes on, this is what my reaction does. I notice right away that my reactants are higher than my products, which are lower. That means that this reaction gave off energy. It's called an energy releasing reaction or exothermic reaction. So endo, take in, exo, give out. All right, so what is a catalyst? Well, a catalyst is a substance that's going to speed up the rate of a chemical reaction. Another word for a catalyst is an enzyme. A catalyst will speed up, or an enzyme will speed up a reaction by lowering the activation energy. A catalyst or an enzyme will participate in a reaction, but it's not going to be changed. So it can be recycled and used in reactions over and over and over again. So if I'm an enzyme, I'm going to participate in the reaction, but the reaction is not going to change my shape unless it's under very specific circumstances, and we'll talk about that at the end. But under normal circumstances, the reaction is not going to change my shape or any of my characteristics. So I'll be able to go and participate in as many reactions as I'd like to. All right, so here is another graph, and this graph is very important. We will use this graph over and over again. You'll see it on quizzes, you'll see it on tests. All right, so let's first orient ourselves. We have on our y-axis energy. On our x-axis, we have the course of the reaction or time. And I have two reactions here. I have a reaction in blue that's a little higher, and I have a reaction in red that's a little lower. Okay? The reaction in blue is the first one that we'll talk about. So the reaction in blue is an uncatalyzed reaction. It's a reaction that does not have a catalyst or an enzyme. This un portion of the word tells me that I do not have an enzyme or a catalyst. Okay? There is a point called the EA point. It's right here. It's the highest point on the graph. This is the activation energy. Okay, it's called EA because EA means energy of activation. Okay, activation energy. The highest point on the graph is where we find the activation energy. And so what that value is the difference between this line, which is the line where my reaction started, how much energy they had when they started. So I want to know the change in the amount of energy from where the reaction started to its highest point. That's the activation energy. Let's talk about this red reaction, red curve. So the red curve shows a catalyzed reaction. That means that there is a catalyst, there is an enzyme. Okay, it has an activation energy as well. It's going to be right here on the graph. So from the baseline or where the reaction started to the highest point on the curve is the activation energy. And if you look, you can see that the uncatalyzed reaction, or the one without the enzyme or without the catalyst, has a higher activation energy. It's all the way up here than the reaction that has the enzyme or the catalyst. It has a lower activation energy. It's all the way down here. So this reaction with the lower activation energy can happen more easily. Therefore, it will happen faster. All right, so what is activation energy? We've talked a little about that. The activation energy is the amount of energy that's needed to start a chemical reaction. So to get that reaction started, we need a certain amount of energy. That's called the activation energy. Catalysts or enzymes will speed up a chemical reaction by lowering their activation energy, just like we saw in the graph. Enzymes, I keep telling you, are catalysts because they're going to lower the activation energy by grabbing those molecules and holding them together so that they can bind and synthesize, become one, or it's going to hold those molecules together and help them break apart or decompose. So here's a picture that shows an enzyme at work. So at first we start with a substrate or a reactant, two reactants. We're going to put them in the enzyme at the active site. That's the place where the substrate goes. And we're going to bind them together into an enzyme substrate complex. That's one of your vocab words. At some point, these substrates are going to turn into a product. And then the enzyme will detach from the product. Notice that the active site is still the same as the active site was at the beginning. So my enzyme is ready to go and catalyze another reaction because it was unchanged. Here's our graph again. I'm hoping that by seeing it again, you'll kind of take a moment to look at it and think about what the energy of the activation energy means. How does an enzyme catalyze a reaction? What does an enzyme do to make the reaction happen faster? Pause the video and try to think through that. Maybe say out loud what the enzyme does to make the reaction happen faster. So reactions can happen without the help of a catalyst or without the help of an enzyme, but they don't happen fast enough to be useful for our bodies. So let's talk about substrates specifically. Remember I mentioned the word substrate a couple of slides back. So a substrate is the molecule that the enzyme is going to bind to. Okay, it's going to bind to the active site. Here's the active site. The substrate is going to bind to the active site of the enzyme. Okay, the reactants of a reaction are called the substrates. All right, so it's going to bind to the active site. It'll become an enzyme substrate complex, and then the products will go away, and the enzyme will be ready to catalyze another reaction. What is the active site? So every single substrate and enzyme have a special or specific shape, and that shape is what binds to the active site. So enzymes will bind to substances based on their shape. That's important. How does an enzyme know which substance it's going to work with or what substance will bind to it? It's based on shape, okay? So if you look at the picture, you'll see that the active site has a shape that is complementary or goes with the substrate. So these shapes are complementary. All right, so the site where that substrate will bind to the enzyme is called the active site. Now we're going to talk about something called the lock and key hypothesis. Enzymes will bind to substrates based on their complementary shape. We just talked about that. The fit is so exact that the active site and the substrate are compared to a lock and a key. And this is what we mean when we say that enzymes are specific. That means that Every enzyme has its own substrate, and they're going to bind to that substrate only, and it's based on shape. Okay, they're specific to their substrate. When the substrate binds to the enzyme is going to change its shape ever so slightly, very, very, very slightly, so slightly that you couldn't even really see it. Okay, you're going to hear this called the induced fit model. So that substrate is going to bind to that enzyme and the shape will change just a tad bit. Okay, you can almost think of this as the enzyme giving the substrate a little hug just to make it fit perfectly. Okay, that's called induced fit. So this picture just goes over the lock and key hypothesis, which again says that the substrate has a shape that is complementary or it fits perfect with the enzyme. If the shape of the substrate is not correct, then it won't be able to bind to the enzyme and the enzyme won't be able to do what it's supposed to do. All right, so when we talk a little bit about vocabulary, I just want to point out to you that digestive enzymes are going to match the foods that they help to break down. So lactase is going to break down lactose. Okay, remember the ASE is the enzyme, the OSE would be the sugar. Here are some that actually don't follow that rule. We have amylase, which we talked about in one of my classes. There was lots of discussion about amylase, and amylase is actually just not in the saliva. There's other places in the body that you can find amylase. There's one other place. So amylase breaks down starch. Pepsin breaks down proteins, and it's called pepsin because the bond in proteins, the bonds between amino acids are called peptide bonds. So that's where we get pepsin from. Sorry, I misspoke. Um, and then we have lipase, which breaks down lipids. More enzymes that break down things. We have sucrase, which breaks down sucrose or table sugar. Now, each enzyme is going to work best at a certain temperature or pH. And first, I want to talk to you just a little bit about pH because there's a picture of the pH scale. So pH is a measure of how acidic something is. So if you think about an acid like lemon juice or vinegar, you're talking about something that's like down here. Okay, so it's like pH 1. Actually, it says on this chart that lemon juice is pH 2 and vinegar is pH 3. Tomatoes are also acidic, they're pH 4. So down below pH 7, which is like neutral pH. Below 7 are my acids, your acids. Okay. When you get to 8, 9, 10, you're talking about a base. Something that's really basic is ammonia, if you've ever used ammonia to clean. If you have ever used like Nair, Nair is really, really basic, okay? Or it's a base. The opposite of an acid is a base. So when you get to the 8 through 14 area, you're talking about things that are basic. Okay, how can enzymes be affected by pH or heat? So enzymes are going to work best at a certain pH and a certain temperature, and that's going to be determined by what type of enzyme they are. For example, if it's an enzyme that works in your stomach, it's going to work at a very acidic pH, so a very low pH. And the temperature is going to be around the temperature of the human body, okay? That's going to be its ideal situation, all right? If we move an enzyme outside of its temperature, that is its ideal temperature, or we move it outside of the ideal pH, then that enzyme will change shape or it'll start to break down. And that is called denaturing. Okay. So when an enzyme has changed shape and it can't work, because remember, it's going to bind to the substrate based on shape. If the shape is different, it can't do its job. So that's called being denatured. So if an enzyme is denatured, it's broken. It can't do its job. Okay. So temperature is one thing that we'll talk about that can stop an enzyme from doing its job. Okay. So if you look at this graph, you have temperature at the bottom, and enzyme activity would be on the y-axis. So when the temperature is low, then the enzyme is sad, it can't work. When it gets to between 35 and 40, that enzyme is at its optimum temperature or its best temperature, its ideal temperature. It's working really well. And then as we get hotter, the enzyme stops working again. This time, the enzyme is denatured. It has changed its shape and it can't work. Okay. It's the same with pH. So here is a graph that talks about pH. When the pH is low, the enzyme is denatured. Okay. If we were to change the pH and add some new enzyme, it's going to start to work. So it's not going to denature all of it until it gets to this optimal pH where it's all working. And then as we change the pH going this way, it's going to denature again, or we would add new enzymes. So we would not change the pH in a sample and see it work. Once the enzyme is denatured, then we would have to get some new enzyme, okay? But as we move along this graph and we talk about a difference in pH, we see that the enzyme is denatured as we approach 10, where it's completely denatured, okay? So essentially, enzymes are important because every reaction in your body is helped by an enzyme. And enzymes are what we like to call the workers of the human body or the workers of living things. Okay. I hope you guys enjoyed this talk about enzymes. I will see you all in class. Have a good day.